Hello to everyone. Today we have Manon from University of Kentucky, and this morning he will talk about the introduction to toric vector bundles.
All right. I think this mic is on. If someone tell me if it's not.
We can hear you.
Okay, great. So this being the learning seminar, I'm going to, in maybe gory detail, go through Klyachko's classification of toric vector bundles and some things that it gets you, and then some questions that I don't know how to answer. And I'm going to try to do it as carefully as I'm capable of. Probably some of you in this room know this stuff better than I do, but I'm going to be as careful as I am capable of being. All right, so this is a toric talk, so let's fix the usual toric notation. I'll work over C for fun. So T is going to be a D, rank D torus. N is going to be the free group of co-characters of T. And of course, N is secretly just Z to the D when you pick some basis of co-characters. And then M is going to be the dual lattice of characters. And this is also Z to the D, and these are dual lattices, so there is a pairing, which I'll just, denote P, say, with this year's bracket, right? So, in the geometry of a torus and its various equivariant compactifications, an integral point in N is a curve in the torus, right? It's a very special curve. And by understanding how that curve behaves at infinity, we can etch out the geometry of a compactification of T. And then the dual lattice are the co-characters, or the characters, excuse me, which are like images of the torus. And of course, the integral points in M correspond to Laurent monomials, which I'll denote T to the character, and they form a basis of the coordinate ring of T. And by picking certain subsets of those, we get the bases of certain nice completions, partial compactifications of T, right? All right, and then, the combinatorial object that we deal with that determines a toric variety is a fan. I'll think about it in the real points of N. And I'm going to take this to be complete. I'm a coward. And I also want it to be smooth. So by smooth, I mean that every the ray generators of every maximal face form a lattice basis. So I'll say more about what that means in a second. But here's a picture. Here's my favorite fan these days that you can have in mind. So this is a complete smooth fan. And for every maximal face, the first two integral points along those rays form a basis of Z squared, right? All right, a little bit more notation. When I write sigma of like a number, I mean take the faces of that number. So these are rays of dimension that number. And these are max faces, max dimensional faces. And then for a ray, I've mentioned this first lattice point. I'm going to denote that V sub the ray. All right. So that's these points in this picture I drew right here. All right. So this is the combinatorial data of a toric variety. Now I'm going to start talking about the geometry that goes with this data, right? So just want to keep my notation the same as in my notes. So for every face in the fan, we're going to get an orbit of the toric variety associated to this fan. So because of the way we picked the fan, this is a proper smooth variety over C. And it's a torus equivariant compactification then of the torus. And so each one of these orbits, they cobble together to make up the boundary of this compactification. And the way they cobble together is determined by this fan. So in particular, if one face is included in the boundary of another, this means that the closure of the smaller guy contains the orbit of the bigger guy. Right. So in particular, the maximal faces are the smallest possible orbits. So these are the torus fixed points. And so that's sigma of D. And then kind of not quite on the complementary side, but the smallest non-trivial faces, the rays, then correspond to the codimension 1 orbits. And so they make the torus equivariant divisors. All right. So these are the orbits. And then you can stick these orbits together to make a nice, in various ways, to make a nice affine cover of the toric variety. We'll give that a name. So I'm going to let U sigma be the union over all the faces tau contained in sigma over these orbits. And this is an affine toric variety. And it can be realized as spec of a very specific ring. And to define that ring, I'm going to let sigma check. So all of these cones, of course, live in N. So if we take their duals, those live in the co-character lattice. So by dual, I mean all the U which pair to something bigger than or equal to 0 for every point in the original face sigma. Right. So this is a polyhedral cone. You can show that it is cut out by the half spaces defined by the rays, the ray generators rather, of sigma. And when we intersect it with the character lattice, we get a affine semigroup. That's what I'm going to tell you in a second. Yeah. So this affine semigroup is the semigroup of lattice points in a polyhedral cone. In fact, a cosimplicial polyhedral cone because of the way we set things up. And so by various, like Gordon's lemma, for example, there is a Hilbert basis of this guy. It's finitely generated. And so we can form this affine semigroup algebra, and that's what I mean by S sigma. All right. So this is the affine cover. You might be aware of the kind of dual description of a toric variety where you start with a polytope. That's a perfectly reasonable way to do things. It's not my favorite though. So, here might be a polytope that you would start with to get that toric variety. And the connection is that for any polytope like this, you can take its so-called inner normal fan. So you think of the inner normal lattice directions for each of these faces, you make those the rays, and then anytime a collection of your facets of your polytope share a common face, you fill in those collection of rays, and that gives you always a complete fan. And I would call that fan projective because it corresponds to a projective toric variety. But the assumptions I've made on sigma have not necessarily made it projective. You can think of this, if you're a symplectic geometer, you can think of the polytope as an image of the toric variety, a continuous image of the toric variety, at least in nice cases. I like the fan description because being a dual description, it kind of explains how limits work in the toric variety. So in particular, which is important for toric vector bundles. I mean, one way to view a toric vector bundle is it's a rule for taking a vector space, hovering over a point in the torus, and sending it to a limit in all the various combinatorial ways the fan encodes. So one way to view the data of a toric vector bundle is matching the way to take limits in a toric variety with the way to take limits of a vector space. And so we should know the way to take limits in a toric variety before we get into that business. That's exactly what the fan tells us. So for example, if we pick a co-character that lives in a particular face, this says that the limit at 0 of that co-character lands in the orbit corresponding to that face. So this guy should be what? Where is that going to be? Is that it's going to be this torus fixed point. Yep.
What's the limit of a co-character?
I will write that in a moment. Let's name this guy P. So P, by definition, is a map from C star to T. Right? There's a distinguished point in T. I'm going to call it 1. It's the identity. And we could consider what happens when we take this co-character and define the curve through this identity and take the limit as t goes to 0. This doesn't make sense in the torus, but now we have a compact, actually manifold in this case, so it makes perfect sense to ask what that limit is. And the fan tells us exactly where that limit will be. So if we start with 1, this co-character will fly right into the fixed point corresponding to the face we picked, the maximal face we picked. So most co-characters take their limits in the torus fixed points.
How am I thinking of that 1 as being in the torus?
It's the identity.
But then how do you know sort of where it is on the polytope?
I mean this to be a kind of model of my toric variety. It's like an continuous image of my toric variety. So I'm thinking of this as the toric variety. So like maybe you could think about these as P1s. These are points. And then there's a 2 torus living in there.
Okay. And it doesn't matter which way you map the torus onto that polytope, that function will always take the identity to the same fixed point.
That one will because of where it lives. So, okay, let's back up. Let's think of this as the toric variety. All right, we have a torus. And the fan tells us we stick 1 tori in. We stick 5 of them in. 1, 2, 3, 4, 5. And then every time 2 of the guys that correspond to the rays that are near each other are there, we like complete them out to P1s and we identify the little torus fixed points on those P1s. And we go just right around the circle in a chain. This is what that might look like, right? So now let's think about this as the toric variety. Now, this is the torus on the inside. I'm going to just pick an identification of that orbit with the torus. And so I can talk about the identity point, right? Now I can go up to this board. I can pick a co-character P. That is literally a 1-parameter subgroup in the torus. And I can think about what that 1-parameter subgroup does to the identity. Right? What does it do? It carves out a curve inside my torus. It's a curve that's as a scheme, it's C star. It's GM. It's an image of GM in my torus. And then I take its closure, right? and I'm going to pick up limit points. And I want to know, where do those limit points live? I have a compactification of my torus now, so they have to live somewhere on the boundary. And the point is the place I picked my co-character from tells me where the limit at 0 lands. So if I pick it at this face, when you go through the little toric machine, corresponds to that torus fixed point. And so its limit at 0 lands in that torus fixed point. If I picked it a little bit more carefully, like if I picked that guy, like balanced right on that ray, it's going to fly off and land on a very specific point on that P1. It's going to land on the point, like, put one, it's, one, so to speak, on that guy. And every torus orbit has a point like that. It's the identity in that orbit. And then you can hit all the other points in that orbit by thinking of moving this curve by the torus action. And so the fan literally tells you where limits go. Yep. No. This completeness gives you a proper toric variety. So in particular, when you take its like closed points, it's actually a compact manifold. It's just not projective.
And if you take the limit to infinity or 0, it's same.
Put in a minus sign. All right, so this is the geometry of the base. Now let's talk about, like, we want to think about vector bundles though. Yeah.
So if I have a fan and it's not realizable as a normal fan of a polytope, how should I be thinking of my little like cartoon?
Same picture.
It's not.
That's right. So just think of, like, instead of, put P1s together for every ray, if it's a surface, or more generally, put a codimension 1 torus in and codimension 2 for every 2 face, and so on and so forth. So, this. Yeah. Yeah, you can do that regardless. So this is if you want to like work through these, this is an exercise. This is in Cox's Little Shink. It's super fun. I mean, you can still build the affine cover, and then you can still verify that it satisfies the right descent condition to give you a scheme. And that's sort of the way you go about it. All right. So before we talk about vector bundles, let's talk about line bundles. So here's a line bundle. I think I already said, yeah, I already said that. So a line bundle is just a, variety over our toric variety, equipped with a map down to our toric variety where all the fibers are affine lines. You can locally trivialize it, and you can do it in a linear way. In particular, when you look at the transition functions from one trivialization to another where they overlap, it has to be a linear, it has to just be multiplication by a number. Well, actually a regular function, but fiber-wise by a number. All right. A nice, I guess it's a theorem in Dolgochev's book on invariant theory, says that any line bundle over a sufficiently nice variety equipped with the action of a connected reductive group can be linearized. So what that means is if I have an action here, I can find a way to lift the action there. And in fact, there are many ways to do that linearization. So you should distinguish between a line bundle, which is like the thing from algebraic geometry, and a line bundle equipped with an action coming from the base. All right, so what I'm going to tell you about is line bundles equipped with such an action. So it's an additional piece of information we choose. And any two linearizations, there's an exact sequence that tells you how linearizations work, and any two such linearizations differ by a character of the group. So in particular, if you're linearizing SLN by an SLN action, it's like unique. but we don't have a simple group. We have kind of the opposite deal in the world of reductive groups. We have a torus, which has a ton of characters. All right.
What was the reference from Dolgochev?
If it's in Dolgochev's invariant theory book, I don't remember. I think it might
Okay.
be chapter 4. But
Okay.
that's just a place I know of where you can
Sure.
prove that, say, a projective variety equipped with the action of a connected reductive group and a line bundle, you can always linearize the line bundle.
Okay. Thank you.
All right, so we want to talk about T linear line bundles. So what should that mean? So to think about them, let's use the tools that we have with a toric variety. Let's think about what we get when we restrict one to one of these affine patches, right? We know that for sort of general reasons that this has to trivialize on an affine patch. But this is a T equivariant line bundle, and this is a union of orbits. And so this trivialization is going to be torus equivariant. So how could we act on a trivial bundle? Like, what are the ways to linearize a trivial bundle? I'll give you a hint. The answer was 3 minutes ago in the stuff I just said. What are the ways to linearize a trivial bundle? The characters. A character linearizes any, that's a choice of linearization. So the way you can think about it is if I know how to act on the base, I just need to figure out how to act on the fibers, and that's given by a regular way to assign a number to every fiber that does the multiplication, but that's also torus equivariant, and that's exactly a torus equivariant regular function on the torus, and that's a character. So what this means is that, so this is going to depends on a character. Which I'll call U sigma, right? It's different for each linearization. And different for different line bundles, of course. But the way we can think about this, maybe I could just borrow this picture real quick, is that for each of these faces, it's like we pick a character. That character in particular is exactly how it acts on the torus fixed point inside U sigma for the maximal face sigma. On the fiber, I mean. Moreover, these characters can't just be any choice, right? When we restrict to the open corresponding to a smaller face, if we restrict from two different bigger faces, the answer has to agree, right? And so what that means when you translate it into character world is the following. If tau is contained in sigma prime and sigma, then U sigma restricted to tau has to equal U sigma prime restricted to tau. And what the heck do I mean by this? So remember, U sigma is a character. It lives in M. M is the dual lattice to N. So you can think of U sigma as a linear function on N. And what I'm saying by this is literally this linear function, when restricted to this subset of NR, has to be this linear function restricted to this subset of NR. So let's put all that together. For each maximal face, we have a linear function, and they have to agree where the maximal faces touch. What's that? So that is the data of a piecewise linear map. It's a map, and it's from the support of the fan to the real line with the property that when you restrict it to any maximal face, it's a linear function. And it's continuous because it agrees on overlaps. All right, and moreover, importantly, it's integral. All right. To make a connection back with line bundles, or to make a connection back with polytopes, if this bundle here is ample, and you take the convex hull of these U sigmas, you get this moment polytope of an ample line bundle on a toric variety. Okay. Yep.
There where you're saying you have a map from the fan to R. Do you mean you have a map that where the domain is the like set of cones or where
The support.
so like for each cone you're mapping each point within the cone?
Yeah.
So where do I see the use sigmas on the right?
On here?
Yeah, like sigma is a cone. So how do I choose which point in the cone to map?
No, you're mapping the whole cone.
The whole cone.
Sigma lives in N,
Oh, okay.
and U sigma is a linear function on sigma.
Okay.
So it's like a linear function that lives above the cone sigma.
Oh, okay.
And the point is the coherence condition that, you know, the restriction of this line bundle to an overlap, U sigma intersect U sigma prime, it has to give you the same data, means that when you restrict U sigma to tau and U sigma prime to tau, it has to give you the same linear function.
So you take the function that you get by restricting that, and that function is a character, and that is your point
Yes.
to a moment.
Yeah. On the moment polytope lives on the M side, which is always a point of confusion. There's two different polyhedral objects you might associate to a projective toric variety, the polytope and the fan. All right, so let's put this together a little bit more. So to a piecewise linear function, I'm going to associate a line bundle. I'll just call it O psi. If psi and if you change psi by a character, a global linear function, this is the same underlying line bundle with a different linearization. And this is the only choice you have. So this is the M in the choice of linearization. So this is the same underlying line bundle, different linearization. All right. Here I'm regarding U as a global linear thing. We can also use this description to describe the T equivariant, the category of T equivariant line bundles. So what I mean by this is a T equivariant map between these, you know, invertible sheaves, if you like. This space is 0 otherwise, and is C if the target is an upper bound of the input. Is this clear what I mean by this? Okay, so these are functions. Does it make sense for one real valued function to always be bigger than another? If that happens, there's exactly a C's worth of maps from this guy to this guy. Yep. That's right.
What was the question?
But T equivariant, and so that fixes it can only be at most 1. The T equivariance here might be a little confusing because I'm going to tell you what global sections are in a second. So when you have here's the point. When you have a description of the category, you can actually say now what global sections of a line bundle are. The category gives you a ton of information. So what are the T equivariant? This is a little weird. I'll put it down here. What are the T equivariant global sections gonna be? Well, really, this is a little illegal. Like I should fix a linearization of O, right? Global sections are maps from O. But this hasn't been linearized. So I have to pick a character. And then I can use this rule, right? So I'm going to pick up a contribution if U is less than psi, and I'm not if it's not, right? Now range over all the different linearizations of O. How many are there? M's worth, right? And so now range all over M, and you have a function. It's like 1 or 0. It's 0 if U is not a lower bound of psi, and it's 1 if it is. What do you think the set of points where there's a 1 look like? It's a polytope. All right. So let me draw a picture. Let me draw an example of this. So we haven't had a good example yet. So let's do P1. The fan of P1 is very nice. And I want to like put a character for C star on each maximal face in a way that they glue together. That's really easy. The characters are just numbers, and they mean the slope of a line over the two different rays. Those always agree at 0, right? These lines always go through the origin. So let's just be easy on ourselves. Let's put 2 and 0. All right. So here's how you can think about this particular line bundle. Where this is like 1 and then it's 2. Looks like that, right? You might be thinking, this is P1. Why does it have 2 numbers associated to it? And that's a completely valid question. It's because we have a linearized line bundle, which means we have to have an extra choice of something coming from M. And what is M? It's Z. So we really have the degree and a choice of linearization floating around here. Yep.
In this T category, this can change as multiple. If you have the same line bundle, you choose different linearization.
Yeah.
Honestly, it's not. You know, the underlying bundle is the same.
The underlying bundle is the same. Think about the sections, though.
Yeah.
What's happening to the sections? They just get shifted by -U. It just shifts the polytope. And this is a thing that we all should remember, that if you take the polytope and you just like rigidly move it around, it's the same. You could always, it's the same thing. That's choice of linearization. On any toric variety, yeah. Every line bundle can be linearized. Yeah, this is not true for vector bundles though. Okay, let's compute global sections. What are global sections? They're lines, and they're lines that have to be below the yellow line, and they have to have integral slope. So we could do 0, that counts. We could do slope 1, that counts. Those are meant to agree there. I just wanted to emphasize, right? Or we could do slope 2, that counts. There's 3 sections. Which line bundle did we find? 2 minus 0 is 2. So this is a linearization of O2. And you could get a different linearization of O2 by change that to -1 and change that to 1. Right? You could still find dupe, 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 right? And that's all changing, adding a character is going to do. All right. Sorry, this is taking way longer than I thought, but I think it's fun, right? Sort of fun. kind of fun. Okay, so I guess I'll just say in words. One of the great success stories then is that you can read positivity properties of these line bundles off this function. So the two you're interested in is like nef slash, is effective, nef, and ample. So in particular, nef is that the function's a convex function. And the ample is it's strictly convex. So that's fun, right? That's pretty fun. And we would like something similar for vector bundles. Okay, so let's just get to the point with that. So a toric vector bundle is a vector bundle over our toric variety equipped with a lift, a linear lift of the action of the big torus. I'm going to let the inverse image of our special point, that's a very special vector space. We're going to call it E. All right. And let's fix the rank of the vector bundle to be R for rank. All right. Klyachko tells us that we can exchange this piece of information with a much more combinatorial piece of information, a subspace arrangement in E that has been decorated by toric stuff. Right.
Sorry, what is E again? It's pi inverse of what?
The identity point in the torus, thought of as a special point of the toric variety. Okay, here's what Klyachko, let me actually make a few comments on this. This is Klyachko's classification from '89. Kaneyama gave a classification of toric vector bundles in '78. That's like earlier, by very carefully studying what the cocycles look like. So for every vector bundle, you can assign a GL cocycle. And, Kaneyama figured out precisely what they have to look like and used this to prove some very nice things. Klyachko came along later. I believe his main interest was the Horn conjecture, which he didn't use toric vector bundles ultimately to prove, but that was kind of his entry point. So here's what Klyachko says. For every ray, we get an exhausting, more like it, exhaustive integral filtration of E. Exhaustive means it begins at E and it ends at 0. It's decreasing, so as the integer goes up, the space goes down. And integral just means that this is an integer. All right. So you give a flag in E. Second piece of information is that for every max face, it doesn't need to be a complete flag. It could go everything, 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 one dimension, nothing. And that's exactly what tangent bundles do. No, sorry. It's just my index. It's my fault. The second thing that we get is a splitting for every maximal face. All right. And the third thing we get is a coherence condition. It says that anytime a ray lives in the boundary of a face, the spaces for that ray have to be built. from the spaces, from the splitting of that face.
Sigma of D, by the way, in the second one, that's the, D is the top dimension. Right?
Yes. These are the three pieces of information. Man, I'm so out of time. What are the what? That's the, it's just what I'm calling the spaces that appear in the splitting.
Oh, okay.
No, sorry, this is, let's call rank R prime. All right. Klyachko also says that the category of vector bundles, torus vector bundles, is equivalent to the category of Klyachko data. So a map, let's just call it F, from, you know, map between these let's just, you know, these data is actually just a linear map where this happens. Just has to stick the filtrations for the domain inside the filtrations for the range. All right. And then Klyachko's theorem says that the category of torus equivariant vector bundles is equivalent to the category of Klyachko data over the fan sigma. All right. So I think I want to move some of this stuff to the next talk. Is that okay? It's like an intro in the next talk. So let me just, in my remaining, like 7 minutes, sketch where this data comes from. Like what is going on here? Because that'll be helpful in understanding what I'll talk about at 1. All right, so let's actually keep that. You know, figuring out exactly what's going on the affine charts was very helpful in understanding why piecewise linear maps classify line bundles, right? So something similar should happen with vector bundles. So our first move here should be what happens on an affine, right? So what we want to think about is the space of sections over a choice of affine. So this is a module over S sigma, right? It's an S sigma module. And moreover, U sigma is a toric variety. Its inclusion into X sigma is torus equivariant. Its space of sections will have a T action. And whenever you got a T action, you should use it. And then finally, we can imagine what's going to happen when I take one of my favorite elements here and I act on one of these spaces here. And what I'm going to write is going to anger you. It's a choice, and just don't freak out. It's a choice of convention. It makes some other stuff work. I hate it. We all hate it. Okay, it's fine. Okay, I'm gonna write everything except the part that makes me mad, which I'm gonna write last. Ugh. We think of V as shifting things backwards. And that's because it makes the other stuff work. There are like 16 different two-valent conventions in this topic. It's the worst. Do you know what 2 to the 16 is? Some number nobody knows, and it's huge. All right, but this you know, this is how we're going to make structure in our toric vector bundle. So here's the point. I'm just going to write it at the bottom here and then I'll slide it back down. If V lives in sigma perp, sigma perp is exactly the guys that pair with everything in sigma to be 0. Then TV is a unit. And then that implies this is equality. All right. So really what we obtain from thinking about the sheaf of torus equivariant sections is we start to get something that looks like an arrangement of subspaces.
Sorry, what is V range over here? What are the possibilities?
V lives in sigma check.
What is it?
So V lives in sigma check intersect M. Right. So really, we ought to think about the space as little blocky U sigma E, where little blocky U is the equivalence class modulo the perp. Right.
Sorry, what is this? Is there a definition of this or is it just
So this is, gamma U for any U and M. The point is that they're all going to be the same modulo, they're all going to be the same if you shift them around by this perp. And so we ought to just think about them as the same space. All right. Now, if we take array, we consider array, then M mod the perp is just Z. And what do we get from this condition? We get a decreasing integral filtration when we put the blocky bits on it. So in this case, gamma blocky U sigma should think about it this way, right? And this guy is less than or equal to this guy. And they both live in Z. And so what do we get? We get a decreasing integral filtration. Yep.
Correctly. So the U and the U minus V, I'm multiplying the seemingly smaller one by a unit. That doesn't seem to do anything. But then how come the other one isn't bigger anyway in virtue of the minus V having shifted it back? Why is that equality when 2 to the V is a unit?
Oh, you can apply it over here too. And they're inverse.
Why would it be inequality if there were no 2 to the V? Why does the U versus U minus V not make the right-hand side bigger?
I don't understand. So this, like, just from having the action of the ring, this has to include into there. All right. That's the beginning of this discussion. But then if this is a unit, you can act here to put it in there, but you can act on this guy to put it in there, and they're inverse functions. And so it's two modules equipped with a module map that's in, where the compositions are identity. So they're isomorphic.
Can you tell me more about what the sub-U is doing?
The sub-U is just the U equivariant part of the module.
Why is the U minus V equivariant part not larger than the U equivariant?
It is.
But not if he's.
Not if it's U.
If it's a unit, they're equal. It's bigger than or equal to. And it's equal to exactly when the V is an invertible thing.
But this sub-U is not an S sigma one, or it is.
This is an S sigma module. It's
One of those is S sigma.
no, oh no, the sub-U is a graded component. Yes,
Yeah.
U is a multigraded, is a choice of multigrade.
And T to V is a unit exactly when U and U minus V are the same graded.
I don't know if that's if and only if. The point is that if you pick something that's a unit, and the units are precisely the Laurent monomials that live in the perp, then this is an equality. That's the implication. So you always have an inclusion in this like arrangement of spaces, but it's actually an equality when this is a unit. And it's because you're allowed to multiply this guy by T minus V, because minus V lives in the ring too, as it is a unit. That make sense? And then the linear function you get by T to the V is then, there's a map back, and composing both ways gives you identity. So they're isomorphic vector spaces.
Wait, so which V's give you units? So
Per-
exactly those. all
Exactly
those.
those.
It's not like if that it's in there and then it's also a unit.
That is
Yeah.
exactly a unit, is a T to the V where V lives in the perp. That is exactly the units of S sigma. I mean, plus C star, right? You throw a C star guy in there too. All right. Okay. One other, let me make one more point that I forgot to make earlier. If you take any of these guys and you take a section and evaluate it at 1 at the identity, you get a point in E, right? If you took a couple sections that had a linear relation between them, when they were, if their images had a linear relation between them, then you could take that guy and smear it all over the toric variety and take its closure in the boundary, and you would get a linear relation on the sections you started with. So what this shows is that each of these spaces is actually a subspace of E. So the map, so something I didn't mention that I should have, is there is a natural way to stick this inside E by taking a section and evaluating it at the identity. And this map is 1-to-1. Okay. So this is where the filtrations come from. I'm sorry, I went over time. Only by 5 minutes. All right.
So how many of these things are there? So like, for instance, suppose I take a toric surface and I take rank 2 vector
Oh, yeah.
on it. So then I have a very small amount of data.
Yeah.
but,
So in this case, a toric surface, you only have to talk about the filtrations. So if it's a smooth toric surface, I think everything should be determined by the filtrations. Why is this the case? So all you got to check is that anytime things share a face, there's a common basis, which will happen because for toric surfaces, you're only ever comparing two rays at a time. And this is a theorem I'll get to at one. So I think for a toric surface, you just have to pick subspaces, one for each ray. And then you have to, label them as a filtration. You have to say where in the integers does that subspace become where it drops from E to the subspace. And then where does it drop from the subspace to 0?
I have another question.
And that data, by the way, where the drops happen is equivalent to picking a total churn class.
So another question I have is, where does it go bad if it's, suppose I don't really want to stick with smooth torics?
Simplicial, it doesn't, you have to just be careful that the, okay, so when you have the data of the filtrations around a face, you can use this to back solve for what these, where did it freaking go? What these characters need to be. You can just do toric stuff and be like, oh, it has to be this, 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 and this. So you just have to make sure that when you do that back solving process, you get a bunch of integral things. So it's like a line bundle where there's just an integrality condition, right? That says the difference between Cartier and Vey. It's exactly like that.
So it's just keeping track of more information,
Right.
or it's cutting out a whole lot of possibilities, because most of the time it won't be integral.
Yeah, it's like omitting a bunch of, it's a check, right? Are these integral or not?
Right.
For a more horrible toric variety, you need the condition that says, when I do this back solving process, I actually can assign a character that gives me these values on these rays, right? It's exactly that kind of condition. So there's ways to assign, what happens for worse singularities is there's no way to assign even a linear function that has the prescribed values on the ray generators, right? So you need that condition. You need to be able to find a linear function and it needs to be integral. No, but the way I built it, like, yeah.
Sorry,
So
what
you
was
need
the
to
question
add-
there?
Klyachko's theorem doesn't depend on smoothness. I'm just working
yeah.
with smoothness to make my life easier.
Sure. And on a surface, if you had on a non-smooth surface, the cones that don't agree are going to give you the singular locus. Is that right?
I don't know what you mean. The cones where you have to be more
No.
careful will be the singular locus that you have to worry about.
Right. I guess what I was trying to figure out is if so you said on a surface I can just pick vector spaces put on or pick subspaces put on each cone on each maximal cone and I'm good, right? Like the rays
right.
are just, yeah.
But then you have to put numbers.
Yeah, okay.
And the
then
way
this
you
is this
assign
is what
those-
goes wrong if I had a non-smooth cone, then
You can't see me. Yes.
yes, I can. Okay, thanks.